Morning student. In this electrostatic charges and field, we will proceed for our next lecture, that is related with the application of Gauss theorem. So in the previous class we have derived the Gauss theorem, and for that Gauss theorem, which states that if you are having a charge and if you enclose that charge by any arbitrary surface that is called as a Gaussian surface, then the electric flux coming out of the Gaussian surface is equal to 1 upon epsilon naught the charge enclosed by that surface. This was the statement of our Gauss theorem, and we have proved that one also. Now we will go for the application of Gauss theorem. So in case of application of Gauss theorem, we have calculated the electric field intensity at any point from the source charge by using the Coulomb's law, and you got that equation, that is electric field intensity is equal to 1 upon 4 pi epsilon naught q into q0 upon r square. So that is the formula for the, you can say, force, and the electric field intensity 1 upon 4 pi epsilon naught q upon r square. That means the electric field intensity is inversely proportional to r square, that we have got from the Coulomb's law. Now if you are having any another charge distribution, so in the previous class we have discussed about the you can say the charge distribution, continuous charge distribution, that is in case of line charge distribution, surface charge distribution, and volume charge distribution. So here first of all you have to find the electric field intensity due to an infinitely long straight charge wire. So here you have taken the wire, this is the wire having infinite length, that means it is extended to both the side up to infinity, and you have to find the electric field intensity at any point near this charge wire. Okay, so if you have to find the electric field intensity at this particular point, or you can say at this particular point you have to find the electric field intensity, then what is the procedure for that one? So the things is very simple. First of all, if you want to find the electric field intensity at this particular point, then you enclose the charge of this line, or you have to consider the Gaussian surface in such a way that it will enclose that particular charges. For example, I have used here Gaussian surface as a cylindrical one. Okay, I have considered the Gaussian surface as a cylindrical one here. Why I have considered the Gaussian surface as a cylindrical? Because you have to choose the Gaussian surface in such a way that the electric field intensity and the area vector both should be either perpendicular, or you can say parallel to each other, so that the angle between them we get 0 or 90 degree, and it is very easy for the calculation point of view. So here I have considered the Gaussian surface as a cylinder, and I have to find out the electric field intensity at this particular point or at this particular point to both the sides from the charge wire. So I have enclosed this much portion of the wire by using the Gaussian surface. So Gaussian surface you have considered as a cylindrical one. So no doubt students, you are knowing that the cylinder is having a three surface. Suppose this surface is surface A, this is B, and the curved surface is C. That means three surfaces you are having. So you have to distribute, or you have to, you can say, divide this figure into three parts. So what are that parts? Part A, part B, and part C. So the total electric flux by the Gauss theorem, total electric flux coming out of this Gaussian surface is closed integral over surface S. So here closed integral is nothing but, here you can say, the cylinder. So closed surface over integral S E dot ds is equal to q upon epsilon naught. This is the statement of Gauss law. Now what I will do this closed integral over surfaces, I will divide it into three parts. This surface integral over S, integral over A, integral over B, integral over C, or you can say you have to take the integral over the respective surfaces. So the sum of all these surfaces will be the closed surface integral. So I have divided this this closed surface into three parts, A, B, C, and I will take the integral of that particular surface. So E dot ds is nothing but E ds cos theta, So for the surface A, E ds cos 90. Now what is this cos 90, or how you have got this 90? Now you see here, at the surface A, that means this surface, the electric field component and the area vector ds having the angle 90 degree. Therefore the angle between this E and ds will be 90 degree, and you know very well cos 90 is 0. Therefore this will get cancelled. Similarly for this surface also, surface B, the area vector in this direction and electric field in this direction both are having the angle 90 degree. Therefore again it will be get cancelled. And the third curved surface, that is surface C, here the electric field intensity and the ds area vector both are in the same direction. Therefore the angle between them is 0. So we can say that only after cancelling these two surfaces here, because of the angle between the two things are 90 degree, that is the electric field vector and surface area vector, and the remaining only this surface, that is EDS cos 0 for the surface C, or curved surface for the curved surface. So ultimately we can say here the electric field intensity, E, I have taken the outside of the integral, and the integral over the surface C, that is ds, that is curved surface area of the cylinder, is 2 pi RL. That is 2 pi RL. This is the curved surface area of the cylinder. So here I have taken out the electric field is as a constant one. Now here is the point you have to keep it in mind. Electric field is constant everywhere. Now let me explain that things with you by this particular diagram. So dear student, suppose you are having this wire and the charges are here. Then from these charges the electric field intensity will be in this direction, or in all the direction you can say. From this charge also, if you take this charge, the electric field will be like this to all the directions. And if you will make here a circular portion, and if you connect for all these charges, then you will get the cylinder. So ultimately you can say this electric field intensity is in this direction, and the ds area vector also in the same direction. So electric field intensity, we can say in this case, the third one coming out of this one is constant. That's why it's taken outside. And E into 2 pi RL. What is the 2 pi RL? 2 pi RL is nothing but the curved surface area of the cylinder. Therefore finally we can say we get here Q upon epsilon naught, that is the Gauss law, Q upon epsilon naught. This becomes, what this will become now? This will become Q upon epsilon naught is equal to lambda L upon epsilon naught. How it has become Q to lambda L? So lambda is nothing but the linear charge density, and linear charge density is defined as charge per unit length. This is the definition of linear charge density. So ultimately the value of Q you can write lambda into L. So you got here lambda L upon epsilon naught. That value I will keep here now. So E into 2 pi RL upon is equal to lambda L upon epsilon naught. After calculating these things, you got this equation, that is E is equal to 1 upon 4 pi epsilon naught 2 lambda upon R. How this 2 lambda you got here? Because here you have multiplied this 2 by again 2, so you got this 4, and therefore once you have multiplied denominator by 2, so you have to multiply numerator by 2 also. So 2 lambda upon R. So what is the important conclusion you will get from this equation? Important conclusion you will get that E is inversely proportional to R. That means if you take the linear charge density, linear charges if you are having, and if you have to calculate the electric field at any point near that charge, near that wire you can say, so the electric field intensity goes on decreasing as you go away from the wire, that is inversely proportional to R. On the other hand, student, in case of Coulomb's law, if you take the charges, isolated charges you can say, or you can say in case of dipole moment or dipole also you have calculated the electric field intensity. So in that case, in Coulomb's law you got the electric field intensity inversely proportional to R square, but here you got the electric field intensity inversely proportional to R. You can also remind that the electric field intensity due to a dipole also on equatorial line, on axial line, what the relation you have got about this electric field intensity on these two position. So here you got the relation, that is E inversely proportional to R. So these things are very important. And in vector form, here in vector form you can write 1 upon 4 pi epsilon naught 2 lambda upon R into R cap. And what is this R cap? In the previous lecture also I have told you, R cap is nothing but the unit vector which is in the direction of the, you can say here, whatever you are considering the electric field. Okay, so that is the value of the electric field intensity in case of a straight long infinite wire. Now we will proceed for the next point. Next point is electric field intensity due to an infinitely long thin plane sheet of charge. Thin plane sheet of charge. Now see, once you are using the word thin, that means it is very having the negligible small thickness. Thickness also you can take approximately equal to the thickness of the charge, that you can also take. And suppose if you are having this sheet here, you have considered here a sheet on which the charges are uniformly distributed. Here the charges are uniformly distributed, and this having the surface charge density sigma. Sigma is the surface charge density, because if you are considering the surface, then ultimately you have to proceed for the surface area, or you can say surface charge density here. So all the charges are uniformly distributed, and now from this sheet you have to calculate the electric field intensity. Suppose you want to calculate the electric field intensity at point B or at point A, here also or here, then what you have to do? You can draw a unit vector in this particular direction also, in this particular direction also, to both the sides. Okay, and now the main thing is that from where you have to calculate the electric field intensity at that particular point, you have to enclose the charges by using the Gaussian surface. So Gaussian surface you have to construct now. And again I told you, whenever you are considering the Gaussian surface, then the important thing you have to keep it in mind, the electric field intensity and area vector of that figure, whatever the three-dimensional figure you are considering, then that figure's area vector of that respective surfaces and the electric field vector, the angle between them should be either 0 or 90 degree for the calculation point of view, because it will make your calculation very easy. So that's why I have considered here the Gaussian surface as a cylinder one. As in the previous case, we have discussed that the cylinder is having the three surfaces, that is these two circular you can say area, and this is the curved surface area. So if you are having A, B and C, these are the three surfaces, then the area vector ds here and area vector ds and electric field vector coming from this charge sheet. Okay, both are parallel to each other. But on the other hand, the electric field here going in this direction and the area vector of the curved surface is perpendicular. Both are perpendicular to each other. Again, what I have to do here? Again, I will split that Gaussian surface into three parts. So the total integral over surface S E dot ds I have divided into three parts, that is the integral over surface A, over in surface B and over surface C. The sum of all these three will constitute the Gaussian surface, that is the cylinder. So closed surface over integral S is E dot ds is equal to sum of all the three surfaces E dot ds. So by using the formula E dot ds, vector E dot vector ds is equal to E ds cos theta. Here the angle between the electric field and area vector ds is 0 for surface A and surface B. So therefore these two will be present, A and B will be present here, because cos 0 is 1, so ultimately that factor will be present there. On the other hand, the angle here on surface C, that is on the curved surface, the angle is 90 degree. So the angle 90 degree is between the electric field and surface area vector. So cos 90 is 0, so this will get cancelled. That means only here 2 will be present. Just to recall the concept of the previous portion, that is the linear charge density, there also you have considered the Gaussian surface in the cylindrical form, but there only one surface is present, that is curved surface, and the other surfaces has become the 0 value. On the contrary, here you can say the true surfaces which were cancelled there, that is present here, and which was present there, it was cancelled here. So you can say finally you got here closed surface over integral E dot ds is equal to twice E into integral ds. Now what is the value of integral ds? Integral ds means here you can say surface area, and that surface area of the circular part is nothing but pi r square. So ultimately you will get 2e into pi r square. This is the value of the, you can say, closed surface integral E dot ds. Now as I know, closed surface integral E dot ds is equal to q upon epsilon naught. So I will compare this q upon epsilon naught now by taking this q upon epsilon naught is equal to, what is the surface charge density? Very simple, surface charge density sigma is equal to charge upon area. Sometimes A they will use, sometimes S they will use, but ultimately you can put the value of the area, that is pi r square. So you will get here sigma is equal to, you can say here sigma is equal to q upon epsilon naught is equal to sigma into pi r square upon epsilon naught, because sigma is equal to q upon area, therefore q is equal to sigma into a, and put the value of a is pi r square. So dear student, by putting the value of pi r square and solving these equations, you will get that, you will get here, that is E is equal to sigma upon 2 epsilon naught. What does it mean, E is equal to sigma upon 2 epsilon naught? This is for the thin sheet. Okay, the charge is distributed on a thin sheet. So sigma E is equal to sigma upon 2 epsilon naught, but here there is no R factor. That means as you have got in case of linear charge density, E is inversely proportional to R. So here you can say it is independent of that one. So this is the formula for E is equal to sigma upon 2 epsilon naught for the thin sheet. And if you take the thick sheet, that means both the surfaces are present, then you can put here E is equal to 2 sigma upon 2 epsilon naught. Cancelling this 2, we will get E is equal to sigma upon epsilon naught, because here two surfaces you are considering, therefore two surface charge densities, that is 2 sigma you will get here. Here you have got only one surface, here you will get two surfaces for the thin sheet. So ultimately you will get the equation E is equal to sigma upon epsilon naught. So student, I hope you understood about this concept of the electric field intensity due to due to an infinitely long thin plane sheet of charge, and electric field due to an infinitely long straight charge wire. So these two concepts are very important. Please go through this one once again, and I hope you might have understood this topic. So how to use the Gaussian surface, etc. So next part, whatever the remaining part, we will discuss in the next period. Till that one, please once again go through this part, and if you are having any doubt, we will discuss in the next class. Thank you very much.